Hello, welcome to a statistics tutorial. Today we're going to be looking at how linear interpolation can be used to help you estimate the median of grouped continuous data. Wow, that's a title that's a bit of a mouthful. But before we actually look at using linear interpolation to specifically find the median, it's probably a good idea if we first look at trying to understand what linear interpolation actually is. Because one of the quirks of this chapter is, or this topic as a whole, is it's actually a very easy calculation to do, and it's a very easy concept at its core. Yet at the same time, there are a lot of students who struggle with it. And I can kind of understand why, because if you just focus on the numbers side of this, you are just ultimately multiplying, adding, taking away, dividing a bunch of numbers from each other, but therefore can get quite easy to confuse yourself and forget which numbers you are meant to be adding, subtracting, multiplying or dividing by each other. Whereas if you take a step back and go back to what's going on behind the scenes with this method, it becomes a lot clearer about why we are doing what we're doing and with which numbers. One of the key ideas behind linear interpolation is the idea of proportion, and a good way of representing this is using similar triangles. For instance, we've got a triangle on the screen right now, and let's say it's got a width of 5 for this example and a height of 3. We could then draw a second triangle that's in this case smaller but crucially also similar. That means it looks similar but is a different size to the original triangle. And let's say for this example as well, the width of this similar but smaller triangle is 2. We might want to find what the height of this smaller triangle is. And that's where the idea of proportion comes in. Because in similar triangles, if you've got two triangles that are similar, whatever scale factor links the widths, which in this case would be what do I have to multiply 5 by to get 2, which would be 2/5. 5 times by 2/5 is 2. Whatever that scale factor is the exact same scale factor you have to multiply the height by to get from the height of the original triangle to the height of the other similar triangle as well. So therefore, if I multiply the widths by 2/5 to get from the bigger triangle to the smaller triangle, I've got to multiply the height by 2/5 as well to get from the bigger triangle to the smaller triangle. Therefore, meaning the height of the smaller triangle is going to be 6/5, or in other words, 1.2. However, this is then applied to the idea of linear interpolation, because what linear interpolation does is it takes two data points. They could be, for instance, if we're not in the world of stats, they should just coordinates on a graph. Let's say we had the coordinates 1, 9 and 6, 12. What linear interpolation does is it says, let's assume there is a straight line joining those 2 points, and then if you're trying to find a new third point that lies in between them, assume that it lies somewhere on that straight line. So let's say we're trying to find the coordinates of the point where x equals 3. Well, what you might notice is that the 2 points on the ends of the diagonal line have x coordinates of 1 and 6, which are conveniently separated by a gap of 5, which is hence why the triangle's got a width of 5. And then they've got y coordinates of 9 and 12, which are conveniently separated by a gap of 3, hence why the height of the triangle is 3. And then if we're trying to find the y coordinate of this unknown point in the, somewhere in between them here, you might notice it's got an x coordinate of 3, which means horizontally it's a distance of 2 away from the point 1, 9. Hence why the width of the smaller triangle in my example was 2. So therefore, you're trying to find the y coordinate of this point where x equals 3. Well, the height difference between 1, 9 and our new mystery y coordinate is going to be the height of this similar triangle. 1.2. So therefore the y coordinate of this point is going to be 9 plus 1.2, which is 10.2. And ultimately that is linear interpolation. That's all there is to it. So if you are trying to then use linear interpolation to find the median, it isn't any more difficult than what we've just done there. All that happens is we just change from talking about coordinates with an x and a y to talking about the data that's in our data set, which you could treat as one of the coordinates in this scenario, and then separately the cumulative frequency as you're progressing through the groups, which could then be treated as the other coordinate in the scenario. Cool. So with all that said, we'll look at an example, but before we do, a couple of things to point out. The first thing to acknowledge is that in some textbooks, or even in some other videos, you might come across a formula for linear interpolation that might look something vaguely like one of these two things. However, in this video, I am not going to use those formulas or even explain how they work at all. And that's because those formulas are not given to you in the formula booklet for Maths A-level, so you'd have to remember them off by heart. And in those few seconds that I showed the formulas on the screen, you might have noticed that they had a bunch of fraction stuff and subtractions in several places, and therefore the problem is, in my experience, students who use those formulas as methods tend to somehow along the way mix up which number needs to be subtracted from which number, and therefore get the whole thing wrong. And unfortunately, as linear interpolation is generally only a 2-mark question at maximum at A-level, if you make a mistake in terms of plugging things in the wrong place in that formula, you're going to get no method marks at all. So we're going to avoid even focusing on that formula at all, although it's worth acknowledging you are allowed to use that formula if you want to go to all the effort of remembering it. But not me. And then the second thing I want to talk about is to point out that there needs to be a separation in your mind behind what is linear interpolation versus what is just something we need to do whenever we were finding median, even at GCSE. Which is, you need to decide which position the median lies in. The first thing to remind you is, well, first of all, if you're looking at raw data, that means you actually have the numbers in the data set themselves, either in a list or in a frequency table, but you know the individual numbers themselves. Let's say, for instance, we're dealing with a list like this. Of course, the list needs to be put in order, but once it's put in order, the position of the middle term in that list will be decided by the formula, if you will, n plus 1 over 2. So, for instance, for this scenario, we have 7 bits of data, so therefore it will be 7 plus 1 over 2, which is 4. So therefore, it's the 4th bit of data in that list that is the median. Which makes sense, because then visually when you look at the list, you can see the 4th bit of data in order is the middle bit of data. But then you also need to be aware of how to deal with median in grouped continuous data, which is primarily the situation that you're doing if you're using linear interpolation to estimate the median. Because the reality is, because the data's in groups, we don't know the individual data points. If this is the case, for the specific exam board that I teach, they accept that you use n over 2 to decide the position of the median data. However, it's worth pointing out, if you use other exam boards, that therefore they might accept using n plus 1 over 2, and in fact there are some mark schemes for some exam boards that end up showing the result if the student had used n over 2 or n plus 1 over 2, and showing both answers and accepting both answers, which all leads to a lot of confusion for students. However, as I said, for my exam board, n over 2 I think is the default position, so that's what I'm going to be using in my particular method in this particular video. But of course, do listen to whatever your teachers tell you to do. So, with all that said, therefore, the first thing you need to do, not anything to do with linear interpolation itself, the first thing you need to do is just decide which position the median is going to lie in. So, in order to do that, for instance, as I've already said before, we are estimating the median. You can't actually find the median itself because we don't know the actual data points themselves. We just know roughly the interval they lie in. We need to find what position that median bit of data is lying in. So to do that, we're using n over 2, but what is going to decide n? Well, that's where frequency comes in. You can either find the total frequency to find the total bits of data in the data set you've got, so I could manually add 3 plus 5 plus 7 plus 5, or the alternative way that some people like to do is they like to find cumulative frequency, which basically means work out the frequency and add it up as you go along as you progress through the group. So by the end of the first group, you've got a total frequency of 3. By the time you've got to the end of the second group, you've got the 3 we had in the previous group plus the extra 5 frequency from the second group, and you've got a total frequency of 8, so on and so forth, working out the cumulative frequency like that. And therefore you realize that the total frequency is 20. That's important because now we can realise the median bit of data will be n over 2, so 20 over 2, which is telling us that the 10th bit of data is where the median is. So writing that down. Cool. What does that actually mean? Well, it means that we then can find out which group specifically the median lies in, even if we don't know what the median actually is. And that's where some people find the cumulative frequency helpful to write down. You won't get marks for doing it, writing down the cumulative frequency. I'm just saying some people find it helpful to have it visually there. And the reason this is important is because by the time you get to the end of a particular interval, you know the full frequency for that group has happened. So therefore, as you progress through the groups, at the end of each group, and therefore the start of the next one, you've reached that cumulative frequency value. So by the time you get to the end of the first group, we've had the first 3 bits of data happen. By the time you got to the end of the second group, the first 8 bits of data have happened. That means we still need to progress further because we want the 10th bit of data. That's where the median lies, and so therefore by the end of the second group we still haven't reached that yet. So then we progress into the third group, and by the end of the third group the 15th bit of data has happened because the cumulative frequency is 15. But therefore that's the end of the group. At the beginning of the group we'd only reached 8 because 8 was cumulative frequency for the previous group. So therefore that tells us the median is in this group here, the 18 to 27 group, because as I said, before that group the cumulative frequency was 8, and at the end of that group the cumulative frequency was 15, and we wanted the 10th. Cool. So as I said, that isn't actually part of linear interpolation. And again, some students kind of get confused because they view linear interpolation as this big scary method because they group this part in as part of the interpolation. And it kind of is, but also it kind of isn't. This is just how do you know where the median is, full stop. So once we've decided which bit of data we want, now we can actually use linear interpolation to find that bit of data. How you choose to go about that is up to you. I'm going to talk about a couple of different ways you have for remembering what to do with the numbers. One of which is to use the similar triangles idea we had before. And that was to say, well, we could view, for instance, the interval values as the horizontal axes values for this triangle. So that means we're saying the class interval starts at 18 and then finishes at 27. That's meaning straight away we know we're dealing with the triangle having a width of 9. And then you can use the cumulative frequency values if you wish as the values deciding what's going on vertically. So we started at the bottom of the triangle having a cumulative frequency of 8, and then the top of the triangle having a cumulative frequency of 15. And therefore, we know the height of this particular triangle would be 7. Cool. But then we are trying to find where the median, which is the 10th bit of data, is going to be. So we draw a smaller triangle and we say we want the 10th bit of data. When we're saying 10th bit of data, what we're effectively saying is we want the bit of data at which the cumulative frequency reaches 10. So this is a cumulative frequency value. There we go, terrible handwriting, sorry. But anyway, therefore we want where the 10th bit of data is happening, and so therefore what we're wanting is a smaller triangle to have a height of, well, the gap between 8th and 10th, which of course is a height of 2. Now all we've got to do is find the width of the similar triangle as well, using, again, a similar idea to before with similar triangles, is proportion. How do we get from 7 to 2? By a scale factor of multiplying, well, it's by multiplying by 2/7. So therefore we also got to multiply the width of the bigger triangle by that scale factor as well if we want to get the width of the smaller triangle, which we do. So therefore 9 times 2/7 is 18/7, writing in exact form. Write in exact form for the moment because that makes it a bit easier to write down while we're doing our working. Also means we don't lose any accuracy due to rounding. But therefore, that's just telling us the gap between the beginning of the interval horizontally and then where the median actually happens. So the final bit to actually find the median is to do the beginning of the interval plus that gap to reach the place where the median actually is. And if you were to do that, 18 plus 18 over 7 would get you 20.2857 blah 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 blah, which means that we know the final answer is the median equals 20.323 significant figures. Now it's worth mentioning in terms of showing the working, the only method you actually need to show is this stuff here. All the stuff I did with the triangle is just to help it make it visually more understandable, to understand why I was multiplying certain numbers by other numbers. But if you get to the point where you're confident enough with this that you don't need to draw the triangle, then don't draw the triangle. It'll probably save you time. But if you find the triangle helpful, then by all means, if it means you get the question correct, do draw the triangle. Okay, and then very briefly, we're going to look at another way of doing the same question because this alternative explanation might work better for some other people. Different explanations are better for different people depending on how you remember stuff. But anyway, so this is an alternative way of doing the same question. If you did get the first method and you're happy using that, do skip to the next part of the video. I've got another couple of details I want to chat about before the end. But anyway, so in this question, we got the same information again as before, except I have changed one bit of information out. I've changed out to mention that the group that the median lies in has a frequency of 7. And that's a bit of information that was effectively told to us, I should say, in the original frequency table. Anyway, once you've realized that, the thing you've got to be aware of is that linear interpolation works on the assumption that the interval you are looking at, all the bits of data in that interval are spread evenly across that interval. So for instance, as there's a frequency of 7 for this data group, we're assuming those 7 bits of data are spread evenly across that interval between 18 and 27. So that means we can split it evenly between 7 bits of data. So there we go, that's roughly a visual representation of the group being split into 7 pieces. That means we can work out what each gap between these 7 bits of data would be if they're spread evenly. And that would be, of course, the total gap of the group, which of course is 9, and then divided by the number of bits of data that we're spreading it across, which in this case is 7. So therefore that's telling us there's a gap of 9/7 assumed to be between each bit of data in the group. Now, we then need to decide which bit of data we want. Well, the crucial thing to be aware of is that before this group started, we had 8 bits of data. So that means before this group started, we'd reached the 8th bit of data. We want the 10th bit of data. So therefore, we want the second marker long of the 7 bits of data in this group. So therefore, all we've got to do to find the median bit of data is we're going to start at 18 and then add on 2 lots of this interval of 9/7 that we said was separating each bit of data in this group. So therefore, it's going to be 18 plus 2 lots of 9/7, and once again, that's just going to be 18 plus 18/7, which is the same calculation we had before. That is 20.2857, etc., etc., leading once again to an answer of 20.323 significant figures. Nice! So that's an alternative way of looking at it if you prefer. Okay, and then to finish off the video, we've got 2 more details that I want to point out that you need to watch out for. The first of which is checking whether there are any gaps between your groups. That's important, first of all, because most of the time if you're dealing with grouped data or data in classes, it's because you're dealing with continuous data. And the reason for that is because if you're dealing with discrete data, it kind of naturally already is in nice convenient categories for you because the data can only take certain particular values. Therefore, if your data has gaps in between, that's a problem because that means there's some gaps that some data values can fall into that then aren't defined as to which group they're going to lie in. For instance, we could get the number 4.2, and the trouble is 4.2, it's not clear which data group that should lie in. So therefore, we need to make it clear. So the way you do that is you look at what the gap between the data groups currently is. For instance, the first group is 1 to 4, and then the second group is 5 to 8. That's important because it means there's currently a gap of 1 in between those two groups, and we need to close that gap. The way you close it is you basically just find the midpoint of that gap, and therefore the midpoint between 4 and 5 would be 4.5. What you do is you then make that the new class boundary for both the group before it and the group after it. So that means the 1 to 4 group is now going to be finishing at 4.5, and that means the 5 to 8 group is now going to be starting at 4.5 instead. And then you can do that for the other group. So 8 to 9, the group from 5 to 8 and the group from 9 to 12, you can close the gap there as well. Again, halfway between 8 and 9 is 8.5. So you make the second group finish at 8.5 and make the third group start at 8.5. And then the last thing is, what do you do with the first group and the last group with their beginning points? Well, there are lots of different rules and ideas behind what you should do there. And it varies exam board to exam board. And even scenario to scenario. Something that some people like to sometimes do is, depending on how much you adjusted one side of that interval, just adjust the other side of that interval by the same amount. So for instance, as we adjusted the 4 to 4.5, we added 0.5 in other words to 4, we could take away 0.5 from the beginning. And then therefore similar with the end group, as we adjusted 9 to 8.5, we took away 0.5, so also add 0.5 onto the end of the group as well. So basically we're adjusting the beginning and the end by the same amount. Cool. So that's one thing you have to watch out for. And another thing you have to watch out for is what happens if you want to find the lower quartile, the upper quartile, and other things like that. Well, it doesn't actually change the linear interpolation part of the method. All it changes is that bit before linear interpolation where you're deciding what position is the bit of data I'm trying to estimate. So, if for instance you're trying to find the lower quartile, you use the formula n over 4 to decide what position the bit of data is going to be in for the lower quartile. It makes sense because we're basically saying the lower quartile is 1/4 of the way along, which makes sense because the word quartile is to do with the word quarter. And upper quartile will be therefore similarly 1/4 away from the end of the data, so therefore it will be 3/4 of n, or 3n over 4, whatever you want to write that as. That's where the position of the upper quartile will be. And then the last thing you sometimes need to find is you need to find a particular percentile, the 20th percentile, the 10th percentile, the 7th percentile, whatever it is. How do you find that? Well, same way you find percentages. The kth percent of something would be k over 100, and then you need to times that as a proportion by n. Cool! So that's how you find those things as well. After that, it's then the same method that we're using before to actually find what that value is. Okay, hopefully you found today's video useful. Hopefully that cleared up a bit of any misunderstanding you had with linear interpolation if you had already come across it before, or if this was new to you, hopefully you found it useful for explaining what it actually is from scratch. Brilliant. I will hopefully see you in a future video. Goodbye.